now being recorded.
Hello everybody, and thank you for joining us for the first installment in our HIS Cyberseminar series. Today we are lucky enough to have Dr. Sue Brantley from Penn State University. Dr. Brantley is Distinguished Professor and Director of the Earth and Environmental Systems Institute at Penn State, and she's here today as the Principal Investigator of an NSF-funded research coordination network, the Shale Network Project, which has been employing HIS for their data needs. So without further ado, here's Dr. Sue Brantley.
Thanks, John, and thank you for everybody that's listening, either right now or in the future with this archived, when the archived version goes online. I'm real happy to talk about this. I'm honored to start off this HIS series also because we've really been learning a lot working with the CUAHSI folks, and we've been excited about some of the forward progress we've been making. So the work we're doing is trying to help citizens that are living in areas where they're worried about water quality or water quantity, potential impacts from hydraulic fracturing. And this project is one where it's a collaboration between several folks from Penn State. You can read them here, and Pitt. I'm trying to use my cursor. Here we go. Okay, Pitt and Dickinson University. And so a lot of what I'm telling you is things that I've learned through these colleagues. So just to jump right in, we have a network of people that are trying to pull together water quality and quantity data, and we've been running a series of workshops. This is a picture of the people that have participated last year in the workshop. We have another workshop coming up in May, and we've also just started working with high school students who've been involved in this project also, and you can see some of the state high students that have been involved. And we've just started a partnership with a high school in West Virginia as well, and we're excited about that opportunity. So as you know, natural gas is 90% methane, and the U.S. Energy Information Administration estimates the U.S. has more than 2,000 trillion cubic feet of recoverable gas. Most of this is actually what we call unconventional gas, meaning that it's found in low permeability formations, shale, coal beds, tight sands, as opposed to the conventional gas, which is when we drill the wells into permeable formations, not into the source rocks themselves. And really, over the last decade, we've discovered how to get the gas out of the shale itself, the source rock. And the success of this approach, which is the use of hydrofracking in horizontal wells, now has led the EIA to estimate that the rate of development of this gas is just going to be huge into the future. So the shale gas plays in the U.S. are shown here. The one that we're most interested in is the Devonian shales up here, and in particular the Marcellus. And this may be the biggest gas shale play in the U.S., and the rate of development of the gas shale has really been extraordinary. Now, the reason that we're now able to get this gas out economically is because of various technological innovations. For a long time, we've been drilling. Hello? For a long time, we've been drilling vertical wells and actually hydraulically fracturing the vertical wells, and the hydraulic fracturing is just pumping in high-pressure fluid and causing fractures to form down here. But we've also learned how to drill horizontally, and so what these new shale gas wells consist of is a vertical well where the well is then turned along an individual shale layer and drilled out for really long, quite long distances, and then it's hydraulically fractured out here. And we've been doing hydraulic fracturing of vertical wells really since about the 1940s, and we've been doing horizontal wells for quite a while, but not the combination of the hydraulic fracturing in these horizontal wells and shales. And this technique really started in the 1990s and then was first used in the Marcellus Shale in Pennsylvania in 2003. This just shows a little bit more of a close-up of the horizontal part of the well, It's blocked off in different sections, and then the high-pressure water is pumped in. After perforating the edges of the well bores, you can see these little perforations here. And then when the water is pumped in, it actually causes these fractures to form. And this is just a schematic, one person's image of what these fractures might look like. And I thought this was interesting. If you talk to the engineers, a lot of us in the field have different mental pictures of the fractures. But this is the name of the game here, is to get these fractures to reach out and extend into the shale as far as possible and create surface area that then allows the gas to escape from the shale and get back into the fractures and then come back up into the well and out. To hold open the fractures, little sand particles are pumped in to hold these fractures open. So that's the new technology that's been developing. And to make this happen, the engineers used hydraulic fracturing fluids. Fluid is mainly water, as shown here. This is from Chesapeake Energy. The actual cocktail that is pumped down into the subsurface depends on the geology and the company and the various constraints. But mostly it's water. Then some of it is sand. The sand is actually the proppant that holds the fracture open. And then there's other components that are put in here, and these are shown here. And this is where all the differences come from one company to another. But most of them have acid. The acid helps the fractures form, helps clean out, dissolve some of the minerals. There are inhibitors to keep certain minerals from precipitating. Excuse me, there's biocides that kill bacteria because the bacteria can actually cause problems in terms of getting the gas out. And then there's gels and other polymers that are put in to give the consistency of the fluid to actually improve the fracturing. And to do this, the water is pumped down at high pressure and in very, very large volumes, something like 3 to 7 million gallons of water per well in Pennsylvania. And interestingly enough, a relatively small fraction of the water comes back. Here it says 10 to 20%. Sometimes you'll hear 40%, but regardless, much of the water remains behind in the well. So this is a figure made by the Marcellus Center for Outreach and Research, and it kind of cycles through. You can read the year the wells were drilled. Here's 07. You can just see how fast this development is happening in Pennsylvania. And there are now more than 6,000 wells that have been drilled. 3,000 are actually, more than 3,000 are actually producing. And this huge development and speed of the development in Pennsylvania has really created a lot of interest, some of it excitement, and some of it pushback in terms of environmental issues. Interestingly enough, if you think about where that last image showed where the wells are going, you can see that they're up here. Here's where State College is. Oops. Here's where State College is down here, down in the Appalachians. The wells are all up in here. Well, compare this map with the next map where I show you a map of some of the exceptional value watersheds in Pennsylvania. You can see that the sweet spot of the drilling, which is up in here, or has been up in here, up in sort of Bradford County, Susquehanna County, really overlies some of the most beautiful watersheds in the state. And there are some environmental impacts. To date, there's very few papers that have been published, peer-reviewed papers that really summarize these kinds of impacts. And this is one that has received quite a bit of criticism, really, because some people don't think that it is quite a fair assessment. But I like looking at it because it's one of the only assessments I know that tries to go through what these impacts are and actually kind of put some statistics on. So take this with a grain of salt. But here's one person's assessment of some of these impacts as it was completed in I think it was 2011. So this is work by Tim Considine up at the University of Buffalo. He reports, from Pennsylvania DEP data that, many of the wells in 08, half the wells had some level of notice of violation, mostly minor, that the violations declined to 2011. He talks about 25 major environmental events, 9 major spills, 8 spills to water supplies, 4 blowouts, some restoration impacts, and then gas migration incidents. So I recommend, if you want to read about some of these, that you can download this from the web. He reports that about 2% of the wells had casing problems, and this is about the percentage that you hear people talking about, and 0.1% probability of blowouts. So these are the kind of incidents that have happened and have started creating public pushback. And it's really interesting to think about the fact that hydrofracking has been used probably to stimulate more than 90% of the oil and gas wells in the country. Most of them were the conventional wells. But since the development in the Marcellus is really when we started to see some of the really large amounts of controversy and public pushback, and it's really gone international as well. So you can look at some different websites to look at some of the violations. This is one that for Pennsylvania. This is another summary from that report I just showed you. And then this is the website you can go to in Pennsylvania that reports the violations in Pennsylvania. And so this is the kind of thing that we're interested in looking at, and I'll be talking about. Well, when we started looking at the problem, we realized that it was very difficult to get your hands on data for water quality in particular. And so we wrote an NSF proposal to the Research Coordination Networks to get funding to create a central and accessible repository for geochemistry and hydrology data. And then we proposed that we would get data from watershed groups, government agencies, industry stakeholders, and universities, and that by working together on a database that this would actually help in terms of educating citizens about the process, educating scientists about it, and being able to make better decisions. So the two goals of my talk are going to be to discuss this effort that we're doing with the Shale Network, and to talk about it in terms of the CUAHSI, because all the data that we're publishing online we're doing through the CUAHSI, and then really to talk a little bit about the science of what you can learn from this kind of approach and what we have learned. So I'll try to do both things. So we're building the database, and we're putting it on a hydro server, which is really just a computer that keeps our data online. And the hydro server we're using is a CUAHSI hydro server. And then you can use Hydro Desktop, which is a tool that CUAHSI has built, to then go out and look at our data. And this is a screenshot from Hydro Desktop that shows many of the data sites, the sites where we have data now in our database. Now, the reason that we wanted to do it with the HIS is because although we knew of a lot of data that was not online, we also know that there is data already online, namely data from the USGS and the NWIS data service, and then also EPA STORET data. And so what the CUAHSI HIS does is allow you to use Hydro Desktop to actually look really around the world for computers that have water quality data in the area that you're interested in, pull it onto your home computer and allow you to use it. So by Shale Network developing a database, putting it on the HIS, anyone that wants to go out and access the data we've put online can then pull in that data along with any other EPA data or USGS data or really anybody else's data as well. And so we're also encouraging other people to do the same thing for this same problem. And for example, at Wilkes University, Tom Barnard's been working to help pull data online on the HIS for the same reason, to look at the issues around hydraulic fracturing. So for anybody that doesn't know, the HIS is really sort of three parts. And what we've been doing is putting data on a hydro server at CUAHSI, so we're publishing the data online. And once it's online, you not only put the data online, but you also put the data, the metadata. Metadata is all the information about the data, so like the who, what, why, where, when, extra information. And then we can use Hydro Desktop to actually go online and find, what data and what metadata are available, and then be able to use it to look at scientific questions. So I'll just be sort of talking about that throughout the rest of this talk. So specifically what we're doing, if you're interested in the nuts and bolts of it, we're finding data, and we're always looking for more data. Turns out that one of our problems is finding the data. There's all sorts of agencies that have collected data that isn't online, and we've been working with agencies to get their data online. We're working with citizen groups to get their data online, university groups, anything and everywhere. We're trying to get it and get the metadata. We then organize the data into the format required with the ODM, and we do this by working with CUAHSI team, and just a great team in terms of helping us answering millions of our questions. We then load it in a relatively straightforward way to upload it, and then we can use their tools to query and look at the data, make sure that we've got it right. We publish the data with in WaterML, register the web service, and then once it's registered, uploaded and registered, we can access it using Hydro Desktop. And so much of the screenshots that I'll show you through the rest of the talk have gone through that whole process. Now, one thing that is kind of new about what we're doing is that we are really pushing HIS in terms of putting in water chemistry. And in some ways, it's easy to do discharge. It's much more complicated in certain ways to do all the different water quality and all the water chemistry components that we wanted to do. So one of our problems is simply making sure that when we put our data in, that we tag it correctly, that we all call it the same thing, we use the same controlled vocabulary, et cetera, et cetera. And the chemistry is truly complicated. You can just see some of the components that we've been putting in. But, obviously, if you think about it, think about all the different organic molecules that could be measured in some of these waters. We haven't even scratched the tip of the iceberg, so to speak, there. And, each of these has multiple names. There's different ways to refer to these compounds. So there's all sorts of sort of complexity. And then we've only put in a few data that are isotopic. And so this is one of the things that we've really been pushing and trying to learn about in terms of HIS is how do you do chemistry online like this? And I think we've moved quite far. So this is what, as just kind of a review, we've been putting stream water, spring water, groundwaters. We had to ask to be able to put injection waters, flowback waters, and production waters in because they didn't have those sample media, those kinds of water were not in the database before we started working on it. As I already said, it can be accessed through Hydro Desktop. And we've gotten our data from published literature, unpublished literature, industry, government agencies, volunteer groups, and university scientists. Really anybody that has some kind of quality control that we think merits inclusion of the data. And here's a screenshot from Hydro Desktop. This happens to be Bradford County up in I think this is where the most number of wells are. And right over here, right under this, is some data from one of the watersheds that our team works with, the Wysox Creek watershed. And everything that we do with the volunteers is facilitated through ALARM, which is a group through Dickinson University. And Candy Wilderman and Julie Vastine at Dickinson work with these volunteer groups, teach them how to take samples, teach them how to make measurements, go over the data quality and the quality control. And then they send data out to professional laboratories to get a few number of chemical components actually analyzed. And so their data is on the web up here in Bradford County. Now, interestingly enough, if you look at this, you can see that there's not that many sites in Bradford County that have barium, strontium, and pH. That's what I actually pulled using Hydro Desktop. And this figure, this next figure, shows you how many wells there are in the county. Each of these little dots is a well. And so one of the things that I want you to go home from thinking about in terms of this talk is that there are a lot of data for water quality and quantity in Pennsylvania, for example, in this area. But the number of wells is so large that I think that we really are not going to be able to keep up in terms of monitoring with the present network monitoring density that we have. Okay, so that's what I just said. Data are plentiful, shown here. These are, as of November 2012, for all the different analytes, you can see the Shale network sites where we have data in black. And then you can see the well density in green, and you can see that there are a lot of wells here. If you look for specific analytes, for example, here's a plot that was actually made in ArcGIS, but the data was pulled from the Hydro Desktop for methane, dissolved methane in groundwaters. And you can take the data right out of HydroDesktop and put it into ArcGIS and then make a map such as this. Each of these data points is scaled, so the size of the circle tells you how much methane is dissolved in the groundwater. And the thing that you should get most out of this plot is that there's very little data here in Pennsylvania. And you can see the data sets that we put into the HIS. This was done by Paul Grieve, who's a graduate student at Penn State. He's been working hard on this. And this is all the data that we can find, all the published data that we can find. There are a lot of data for Pennsylvania for methane and groundwater. And it's not been published as far as I know. You'll see it in talks. You'll see it in some industry publications. There are homeowner wells data sets that have been collected but that are maintained confidential. And so this is another one of our problems in that sometimes there are data, but there's no way, at least so far, that we've been able to get our hands on it to get it published. And that's one of the things that we've been trying to work at in order to look at this problem. But we'll come back to this map in a little bit, but I wanted to make that point. All right, so let's talk about some potential contaminants. First of all, one of the things that a lot of citizens, non-scientists, are worried about is the stuff in the fracking fluids, the stuff that's injected down. Likewise, people are worried about the drilling muds, cuttings. They can actually also get into the, presumably could sometimes get into groundwater, could have spills. There are emissions from all the diesel motors, electric generators into the air. There's impact on water from that kind of atmospheric emission. There are natural sediments, runoff, just because of the moving earth around and the heavy equipment. Methane that might be getting out of the wells, and we'll come back and talk about all of these. Natural and injected contaminants that come back with the gas. So one thing that you'll learn or hear about or may have already heard about is that as the gas is extracted and comes back to the surface, it comes back up with water. Some of it was water that went down, was injected, but some of it is natural water from the formation, and there are contaminants in that water as well. So I'm going to more or less talk through these and just give you some examples of these different contaminants through the rest of the talk. So what are the impacts of injection and fracturing process itself? First, muds during drilling. I wanted to make the point that it's not just the drilling that we're worrying about. The truck traffic, pipeline construction, of which there's a lot going on right now in Pennsylvania, can all cause natural sediment inputs to waterways. And there's a really nice paper by Pat Drowan and Margaret Brittingham in 2012 where they looked at the slopes of most of these well pads and concluded that 50 to 70% of the well pads are on slopes where erosion is going to be exacerbated by this kind of development. So this kind of natural sediment going into waterways is going to possibly be a problem. But back to drilling muds, this is one example that you can look at the data online by pulling it from HydroDesktop. This is mud release that went into Larry's Creek. Larry's Creek is a very high quality stream in it's near Lock Haven, and I think it's in Lycoming County. And in the week of 10/19/2011, Anadarko was drilling, and as I understand it, there was an accident that they termed fracking out, and some of the drilling mud got into the stream, and you can see some of the impacts here. And it turns out that downstream of this event, the Susquehanna River Basin Commission had a sensor, and so you can pull that data from HydroDesktop, and that's shown here. So again, this is a screenshot from HydroDesktop. And this is once you pull your data, you can look at it. The HydroDesktop will plot it in turbidity in this case versus time. The day of the spill was right here. So ostensibly these would be non-spill related, and then something in here is spill related, and we've been discussing this and thinking about how to think about that. I show the same data blown up right here. And when we've talked to Andy Gavin of the SRBC about their turbidity sensors, he thinks that the sensor was fouled in here, and so he's actually unsure whether these spikes are the turbidity event or whether this whole background increase here is the event. But something in here is that Anadarko event, and needs to be looked at a little bit more clearly and investigated a little bit more thoroughly. Let's talk about the next type of contamination will transport through porous media or fractures, bring fracking constituents into near-surface drinking waters. I'm going to talk about a couple incidents on the next slides. None of these can you pull up on Hydro Desktop. I just wanted to include these sort of for completeness. The only two cases that I know of were at least alleged cases where fracking components that were injected may have gotten into groundwater. One was in West Virginia. This was in 1987. And you have to go back into the EPA sort of old report to read about it. There's no data in that report that you can put online because we would have done that if there was data that we could have done. The thought of this particular case was that a well was fracked and then there was old abandoned wells around it, and some of the fracking components allegedly came back up in a homeowner's well. And so that's a case that is not free of controversy. The American Petroleum Institute calls the report inaccurate and careless, but nonetheless, it's one case that people do discuss occasionally. And it gives me a chance to mention that it's important to note that in many of these states, and in particular in Pennsylvania, there are many, many old wells. Pennsylvania has 350,000 oil and gas wells that have been drilled, and let's see, the location of 100,000 of them are unknown. So in this map, the red ones are active wells, the blue are inactive wells, and the black are abandoned, and then there may be 100,000 more that we don't even know where they are. So this problem that may have been important in this West Virginia case, namely the abandoned wells bringing frac fluids back up to the surface, is actually a very big problem, especially for Pennsylvania or any of the states where drilling has been so prevalent for such a long time that in many cases we don't even know where the wells are. The second case is an ongoing case in Pavillion, Wyoming, and you can read online everything that I know about it. I haven't worked out there, and I haven't really gone into the data in a big way. The EPA has worked on it. The USGS worked on it, but there hasn't been any final reports coming out. The fracking in this case was much more shallow and is a little bit different than what's going on in Pennsylvania. But the reason to go through those two is to really emphasize that there is no evidence that what goes down in the fracking, the injected components, has ever come back up into the groundwater, except possibly for those two cases, at least that I know about. There have been some cases where in the Pennsylvania drilling area, researchers, namely Beth Boyer, Brian Swistock, and others at Penn State, looked at groundwater quality before and after drilling. They looked at, let's see, nearly 230 samples from wells within 1,000 feet. These are within homeowner wells within 1,000 feet or further from Marcellus wells. And only one well showed any before and after change in water quality for a relatively short time. In contrast, 40% of the wells failed at least one of the drinking water standard even before the drilling or even before any Marcellus drilling. And background methane was found in 24% of the wells, and this background methane didn't have anything to do with the Marcellus. All right, another question you might ask is, can fracking constituents enter near-surface drinking water resources through spills? And here's an actual picture of a well pad in West Virginia, and the gas comes up and is with water, and the production water is a mixture of what is pumped down and then formation water from the subsurface, and it's very, very salty. And so there is problems in the fact that it's stored and then transported and disposed at the surface. So this is a nice paper by Wilson and Jeannie Van Briesen where they looked at the volumes of this produced water. It's called flowback water, right after it's been fracked, and it's called production water once the gas is being produced. But you can see these are barrels over time in Pennsylvania. A lot more of this flowback and production water is now being produced and stored at the surface of Pennsylvania. So some of the hydrofrac constituents do come back in the flowback, and you can pull that kind of data using HydroDesktop. So this is another screenshot. Here are wells across Pennsylvania. These are gas wells across Pennsylvania, data from the industry from a publication by Hayes, where you can actually pull the data and get the injection water chemistry and the flowback and production water chemistry. And let's see. Looks like I lost a graph here. Yeah, looks like something happened with this particular slide. Maybe on the online version we can fix this. But the plot was supposed to show benzene concentration versus time. And in this particular case, this data shows that some benzene, presumably benzene that maybe went down during injection, was coming back and was being stored in the flowback waters at the surface. So these are all the different kinds of flowback and production waters that are currently in the database. We have data from Hayes. This is industry data. We have data collected by Carl Kirby at Bucknell and his students. This is data from Pennsylvania DEP from the 26R forms that the only way Carl could get the data from the Department of Environmental Protection was in paper form, so this was all data that then was typed in by his students, and now we've been able to put it in the database. We've put in some brine chemistry from Haluzak et al. This is a paper published in 2012, Applied Geochemistry. And then these are new data sets that we're putting online. So we're starting to get a pretty good data set online for the flowback and production water chemistry. Does development of shale gas cause natural gas to enter the drinking water? There are many pathways for methane to enter drinking water, and this has been known for a long time. And this is a small schematic from the Pittsburgh Area Geological Society. There are many ways for methane that forms at the surface biologically to move and get into well water. There are ways for methane formed at depth to naturally move and get into well water. And then there are ways for methane to get out of a well and get into well water. So there are multiple ways for this to happen. And perhaps one of the biggest problems in terms of the drilling is the casing of the wells. Every gas well is cased with steel and cement, so that the part of the well that goes through the aquifer, the drinking water aquifer, cannot communicate, and so the gas inside the well cannot get out to the water inside the aquifer. And one of the problems is that this casing does not always work, the cement doesn't always work. And a review of the violations in Pennsylvania DEP that Dave Yoxtimer did showed that from 2008, I think, to 2013, the casing or cement, the rate of problems was about 3.1%, and you can read what some of the other statistics were for these other incidents. But this is one of the problems, and then they have to go back in and fix the casing, fix the cement, so that they ameliorate any kinds of issues. But you can see only a very few cases were reported where there was some methane migration into groundwater. There's been a very highly cited and interesting paper by Osborne et al. In Proceedings of the National Academy of Sciences. This shows methane concentrations. This was in about, I forget how many wells right now. I'm going to guess about 60 wells, groundwater wells. And this was plotted versus distance to the nearest Marcellus gas well. And they showed that this was up in Susquehanna County, Bradford County, a couple wells up into New York State, groundwater wells up in New York State. What they argued was that outside of a kilometer, they never saw higher methane concentration in the groundwater wells. But then within a kilometer of the Marcellus wells, they started to see these high concentrations, and they looked at the isotopic signatures and could really argue that they were fingerprinting and seeing that there was Marcellus gas getting into these homeowner wells. Now this is the area where some very high-profile incidents have happened. Cabot has been cited for having problems with many of their wells, and so there is some question about whether these problems now have all been fixed. I know that many of the Cabot problems have ostensibly been fixed, and EPA has reported has been fixed. So this may have been a short-term problem, but it's very hard to tell because, oh, here's another one that we're missing. because I was going to show you a histogram of all the different data that's shown on this map here, but there are very many cases, as I've already been alluded to several times, of methane in the groundwater. And so in New York State and West Virginia, you can see the data. We don't have data that's been published for Pennsylvania, but data that has not been published, where people have sort of published compilations of it or summaries of it, show that this kind of distribution of high methane in homeowner wells is very common, especially up here in Pennsylvania, where the Osborne study was completed. So one of the problems is that it's hard to really pinpoint whether any amount of methane that's in some homeowner's well is actually due to a new Marcellus well, or if it's really related to something that has been there for a long time. And I did have a histogram of that, but I'm sorry that's not showing up. The regulations right now are that the Pennsylvania drilling companies are supposed to, or they can choose to test the drilling water supplies within 1,000 feet before drilling, and Osborne has suggested that that should be extended to 1 kilometer. Companies don't have to give their data to the Pennsylvania DEP, but if they want to use it later to defend themselves, in other words, for legal reasons, then they have to give it to the DEP. So that's what's happening, and they're giving it to the DEP in paper form. They keep their data. The companies have a very large, extensive database as well, and it's an electronic database, and would be lovely if they would share that data, and that's something that we've been advocating for, but we have not been able to see the electronic data. We can get some of this data in paper form, but once again, we have to do what Carl Kirby and Bucknell students did, and type that in essentially by hand. We're working to get an MOU, a Memorandum of Understanding with Pennsylvania, to get some of this data, because as you can see, we do need the data to understand the problems. So what's in the flowback and the production waters, and what happens to it? As the water comes back, it changes its chemistry. The chemistry changes. This is chloride concentration in milligrams per liter times 10 to the 3, so up to, in this particular case, 70,000 parts per million chloride, just as a function of several days after the well was opened, after it was opened at the wellhead. It can actually reach above 200 parts per million, and the brines are mainly sodium calcium chloride brines. They tend to be relatively low in magnesium and sulfate. They have distinctive amounts of bromide, sulfate, and barium, and these turn out to be kind of signatures of the flowback. And all of these components tend to increase with time, and some of the components actually decrease with time. And you can explore this on HydroDesktop with the data that we have input. So why does it come back salty? Well, this is what we think. Beneath the Marcellus is the Salina formation. The Salina group is an evaporite, sodium chloride, so halite salts. And this just shows you the salt thickness in feet in the subsurface. And so all throughout Pennsylvania and parts of New York State are these very salt-laden waters, and they have moved up section. And we think that there is some brine in the Marcellus formation, and some of that salt comes back up in this flowback water. So there are problems with the volume of flowback water and this high salt content. There have been spills. There have been discharges of this, and in particular before 2011 it was legal to take the flowback water and give it to publicly owned municipal water treatment plants, and then they were discharging it into some of the river. And it was simply too high in total dissolved solids for it to be discharged in that way. So although it was legal to do up until 2011, it was not a great thing to do, and there were some issues surrounding that. And you can try to go in and look for these issues online with the HydroDesktop. Then there was some fairly high-profile incidents around bromide, and I'll show you that from the HydroDesktop. So here's a screenshot of bromide versus time in the Pittsburgh Water and Sewer Authority intake, and this is the Allegheny River. And this was one of the rivers where brine was being discharged legally up through 2011. And you can see here this is dissolved bromide in parts per billion going up and down. And if you use HydroDesktop and also pull up discharge, you can see that the up and down of the bromide is related to the differences in the discharge of the river. So there was a relatively constant discharge of brine into the river, legally, as I keep mentioning, but as the water, as the rain and the discharge of the river went up and down, you see differences in the concentration. The problem with the bromide is that it can actually combine with natural organic matter and disinfectants used by the municipal water treatment plant to create sort of brominated organics, which can be problematic for human health. And so in 2011, it was agreed upon that this discharge of Marcellus flowback through these municipal water treatment plants would cease, and then it's supposed to have stopped as of 2011. Oh, here's another graph that's not showing. This is a figure that shows bromide versus time for all the data that we could find for the area, that shows that it still looks like bromide is higher in many of the rivers around Pittsburgh than it was before, let's say, 2009. And this is a little bit puzzling because we would have expected that it went up between 2008 and 2011, but then when they stopped discharging, it should have come back down. So this is a little bit of a puzzle that we're still thinking about. The new treatment regulations say that the discharged water must have total dissolved solids less than 500 milligrams per liter, and you can read the chloride and the barium and the strontium. And so it's no longer being discharged as it was before 2011. You can see here where some of the plants were that were discharging. The dark blue are some of the centralized treatment plants for flowback from conventional wells, and the light blue dots were some of the places that stopped taking waste in 2011. And one of the things that we're working on with CUAHSI, HIS, is we're going to be putting some of these locations, the shape files for these locations, into a customized version of Hydro Desktop, so that people that want to look at the river chemistry and understand why it might be high in chloride will actually be able to look and see where these plants are, and be able to think about it in terms of the timing of brine release. I don't want you to think that Pennsylvania is doing nothing in terms of trying to improve what's happening in terms of environmental issues. There have actually been all sorts of movement in the last several years, including movement towards away from using clean water for fracking and moving towards using sort of wastewater for fracking, or even acid mine drainage for fracking. There's been a big move towards recycling and actually using the flowback water itself to frack. And the latest figures that we've seen suggest that 90% of the water that's coming back up is being pumped back down to frack, at least in Pennsylvania. New linings for well pads. And then there's also, as you may have heard, a lot of the brine is pumped, or some of the brine is pumped trucked rather to Ohio and pumped down into deep injection wells. And so this has kind of been evolving over the last several years. So what about the long-term or cumulative effects? Are we seeing rises in the long term? And I'm afraid to look at these slides because I'm afraid maybe some of these graphs won't show either. I think one of the things that's interesting is to look at the strontium, barium, and bromide. These are fingerprints, I think, are pretty close to being fingerprints of Marcellus brines. Of course, the components that are most concentrated are sodium, calcium, and chloride. And so if you want to look for something that has a brine impact from Marcellus brine, you would also look for sodium, calcium, and chloride. But there's a lot of ways that sodium and calcium and chloride can go into a natural water, and there's fewer ways that you get strontium, barium, and bromide. So just kind of as a slight aside, one of the things that many of us are thinking about is, as you probably know, Pennsylvania has been mined for coal for a very long time, and this shows the map of Pennsylvania and all the coal mines in Pennsylvania. This is, again, from Pennsylvania DEP. And we also have acid mine drainage from the coal mining. And this is from a paper by Pete Raymond and Raymond and O in 2009. This shows Susquehanna, the sulfate concentration. It's actually a flux, so grams of sulfate in the Susquehanna per year versus time. This is in the red. And you can see that since about, whatever that is, 1940, 1950, the sulfate flux out of the river has been going down. And Pete Raymond has argued that this is basically a lag. Obviously, there's very little data back here, and this is a model that they developed. But they've argued that it's a lag. Here's the anthracite coal production out of Pennsylvania, which peaked back here. And you can see the acid mine drainage and the sulfate flux in the Susquehanna is improving now because this energy extraction has been decreasing. And so many of us are wondering and hoping and trying to work to avoid similar kind of cumulative impact from shale gas exploitation. And so we want to be able to look at this kind of data, long-term data, to look for that as well. So, yeah, this is what I was afraid of. I have 3 slides here that you just can't even see. And basically what we've done is used HydroDesktop to pull the data and look at barium versus time for all the counties in Pennsylvania where Marcellus drilling is ongoing. And we've done it for barium, strontium, and bromide. And given the fact that many of these waters had fairly high concentrations of some of these components already, it's hard to really understand whether there has been a cumulative impact or not. Another problem with analyzing the kind of data is that some of the data sets go way back, but then haven't continued into the present, and some of the data sets where analyses have been made in pertinent places in the pertinent rivers don't go back very far, and so it's just difficult to really come to any conclusions. But that's what we're all working towards to sort of understand. So hopefully, maybe in the online version, we can make it so that these figures show. And I think this is my last slide. Let me just conclude by summarizing. This is a huge play, the Marcellus play, but these shale gas plays are going to be developed all over the world. I think that this is something that's just going to start happening, and all of us have to think about the environmental impacts, and I think we need to figure out how to do it in ways that are safe if it's going to happen. There's only 2 cases that I know of, and they're still controversial, about frac fluid components getting into groundwater. But one thing I didn't say, and I'd like to emphasize, is that it's very hard to analyze for many of these organic compounds, and these compounds can change in the subsurface. So, it kind of remains to be seen whether we will ever see frac fluids getting into groundwater. But it certainly has not happened to date. Or if it's happened in a very small number of cases. There are many different ways for components, contaminants to get into groundwater, and I talked about many of them and showed you ways that you could use the CUAHSI to look at these. The states are working very hard to understand some of these problems and to institute improvements in terms of regulations. I think in terms of the HIS and the Shale Network database, there are a lot of water quality data that are available. But these data are hard to access. There are many different entities that have collected the data, and they're not all online. And what we are hoping is that what we're doing will actually be helpful in terms of many people looking at the data sets. But we're also hoping that it's an example of what can be done elsewhere in terms of getting data pulled together. We would not have been able to do this without CUAHSI. The tools that they're building, I think, are wonderful. They're not as problem-free as a commercial entity like ArcGIS or something like that, but they really work pretty well, and they help you understand the data once you can pull it all together. We don't see many examples of environmental impact that are irrefutably related to unconventional shale gas development so far in the database. But as I've emphasized throughout this talk, the densities of sample or sensor sites are very low compared to the well density. It's very difficult to determine the background. And in many areas of drilling, some of the waters already had contaminants before the drilling happened. And so I think that we need to continue collecting the data. We need to demand that people put their data online, whether it's data collected by the industry or data collected by government, even homeowners that keep their data confidential. I think we really need to get this data online. And we need more sampling and chemical analysis. And I want to tip my hat to the Pennsylvania Department of Energy Environmental Protection. They've instituted a new monitoring effort, which they sometimes shorthand call it the STAC 46. And they've been doing this all over the area of Marcellus. And they've been doing this precisely in order to be able to make sure that we're going to be able to see any impacts that might happen or that are happening. And if you're interested in what we're trying to do and you want to contribute, we'd be more than happy to take volunteers or to help you get started. We need help finding data, formatting data, and looking for issues in the data set. And I'd like to thank the NSF for the funding. So thank you very much, and I really apologize that those graphs didn't show up. I've never had that happen before, but we'll try to get that fixed online somehow. Thank you.
Well, thank you very much, Sue, for the great presentation. I'm always a big fan of the Shale Network because, you know, it's a great example of science actually being conducted with the HIS. So if anyone has any questions, please do type them into the chat box. And since we have a couple questions already for you, Sue, I'm just going to read them aloud and hopefully have you address them. So, Sue, a question from John. Might the high bromide, is that, yeah, bromide?
Yes, bromide.
Bromide recently observed in the Pittsburgh River be from upward flow from depth in low elevation valley bottoms via vertical fracture zones?
Hey, John. I'm not, well, you know, the answer to a question like that is always yes. You know, anything could be happening. Do I think that's what's happening? No, I don't really think so. Many of these rivers around Pittsburgh have many influence into them out of coal mines, you know, various pits and wells and various kinds of things. I think that I think we don't know what's really going on, but I'm not sure that I believe that bromide's coming up from deep-seated fractures. I do know there are some natural seeps and some brine seeps into these rivers, though, so, you know, you're right to ask that question, but I'm not sure if that is going to be the answer. You know, there have been some cases of illicit activities. Some truckers have been cited for dumping brines. I know there was a case cited within the last month, I think, where some brines were being dumped in one of the rivers. I think it was the Mahoning River, if I'm not mistaken, that was upriver from some of these sites. So I think there's various things that might be explaining the high bromide, but at the moment we're still scratching our head.
So we have a question from Madeline that's actually a pretty common question in terms of HIS. How do you handle QC issues in terms of inputting and retrieving data from HIS?
Okay, the question of quality control, quality assurance is always a really big one with you know, online data like this. What we've been trying to do is, I mean, first of all, let me tell you my philosophy. My philosophy is that published data has problems in it as well as unpublished data. And when you get published data and you look at it, sometimes you can't see the problems. But it's gone through peer review, so you have a little bit of more faith in it. But often what happens is you play with the data, you work with the data as a scientist, and you can find problems in the data. Or if it looks anomalous, you start questioning it and wondering it, and you try to think of ways to test it. And so one of my basic philosophies is that we have a really big problem right now in that we can't get our hands on data. It takes inordinate effort, you know, time and energy to get data and pull it together, and that we should really almost err on the side of getting data out there and then let people like Madeline Schreiber and John Washington get their hands on the data and look at it and try to figure out, you know, what they think about the quality control. So that's kind of like one of my basic philosophies. But then beyond that, we work with entities that are getting their analyses done professionally and commercially. So we've worked with the DEP. We've just got Fish and Boat Commission data. The Susquehanna River Basin Commission is, has a lot of quality control, quality assurance. So we work with entities that we know that the QC, QA, is reputable and defensible. And then we also feel strongly that we may never have enough sampling sites in these areas to keep up with the potential for impact from wells. And so we really want citizen scientists to participate and to watch their watersheds and to take samples. And this is the philosophy of the group ALARM, A-L-L-A-R-M, which is run by Candy Wilderman and Julia Vastine out of Dickinson College. And we partnered with them early on so that we could get data from volunteer groups. And these groups are working actively with ALARM to know how to take water samples, to know how to make the on-site analyses that they make, which are pH and specific conductants. And then they also take samples. They know how to take samples. Those samples are sent to commercial laboratories. So we're working with entities where there already is a QC and a QA procedure. And you can, when you pull up the data, you can see where the data came from. And if you want to get rid of all the volunteer data, you could do that. But we're trying to not necessarily make all of those decisions for you. We're trying to get the data out there as best we can. And then the more that anybody works with it, the more we find little mistakes. Everybody does make mistakes, and we found some of our own. And if people look at the data and email me or email us about it, then we try to fix it, because it's all about just getting it out there for people to look at.
Do we have any more questions for Dr. Brantley?
John, will we be able to put the graphs on there in the YouTube version?
Yeah, we'll be able to at least put the presentation up, like a PowerPoint or a PDF. So there'll be something up there that includes the graphs as well.
Okay, that's great.
Well, thank you, everybody, for attending today, and especially thank you to Dr. Brantley for presenting. Like I said, it's a great example of HIS being used directly for science. And we have another talk coming up same time next week, where we have Dr. Dan Ames of Brigham Young University, who actually leads the development of HydroDesktop. And he'll be discussing, what new features are available and what new features will be coming in the upcoming weeks and months. So thank you again, everybody, and hopefully see you next week.